Welcome to this video lecture series on group theory. Myself Sudhakar. In the previous lecture, we discussed about elementary properties of groups. In this lecture, we shall solve some important short answer type problems related to the concepts and properties of groups which we have discussed in the previous lectures. So the first question is, define a group, give an example. So to define a group, you remember 3 points. So the first point is, we have to consider a set and it must be non-empty set, and also we must have an operation star. Along with this, G must satisfy 4 laws. So what are those 4 laws? So we shall remember like this: class, ID, in-laws. So class means closure and associative, ID means identity, in means inverse. So if you remember these points, you can write or define a group like this. So we shall write a non-empty set, G together with an operation star, is said to be a group if it satisfies the following laws. So what are the laws we should write? So we shall write one by one. The first one is closure law. So first one, closure law. So what is closure law? A star B belongs to G for all A comma B belongs to G. So second one is associative law. So what is associative law? A star of B star C is equal to A star B star C, and it must be true for all A, B, C belongs to G. So the next is identity law. So for every, or we shall write, there exists an element E belongs to G such that A star E is equal to E star A is equal to A. And again it must be true for every element in G. So next law is inverse law. So what inverse law says? For every element A belongs to G, there exists A inverse belongs to G A star A inverse is equal to A inverse star A, which is equal to E. Here A inverse is called the inverse of A and vice versa. And in case of identity element, we call E as the identity element. So if you write all these four laws, we say that G is a group. Now we shall give an example. So example, what are the examples of group? So the first example is, we can write Z plus. If it is enough, if you write one example. Okay, another example, we can write it as Q plus, similarly R plus and C plus, etc. Okay, now we shall move to the next question. Define a Abelian group and give an example. Okay, to define Abelian group, so we have to consider a group. So group means it has already satisfied four laws. Along with four laws, if it satisfies another one law, that is commutative law, then we say that G is a Abelian group. So we shall start like this. A group G star is said to be a Abelian group if it satisfies commutative law. So what is commutative law? That is A star B is equal to B star A, which is true for all A, B belongs to G. Okay, once again we shall give examples. So we can give example, same example what we have given in group Z plus, because it satisfies commutative law, that is A plus B is equal to B plus A. If you want, you can give R plus. Again, it is true in case of addition, etc. Next question is, define a semigroup. Give an example of a semigroup which is not a group. So we have defined G is a group under the operation star if it satisfies four laws. So four laws. So semigroup means it must satisfy half of this, that is only two laws. So what are those two laws? So first one is closure law and second one is associative law. Therefore we shall define semigroup as a non-empty set. Okay, don't start with a group G star. So a non-empty set G with an operation star is said to be a semigroup if it satisfies the following laws. So following laws. So how many laws? Only two laws. First one is closure law and second one is associative. Okay, if any non-empty set with an operation star, if it satisfies closure and associative, then we say that it is a semigroup. So now you see the second part is give an example of a semigroup which is not a group. So in previous two questions we have given Z plus, Q plus, R plus, etc. Those are all groups because it satisfies all the four laws. And here semigroup means it must satisfy only two laws. All the group satisfies two laws, closure and associative. Therefore, all the groups which we have given in the previous two problems, those are the examples for semigroup. But here in the second part, they have give an example of a semigroup which is not a group. That means we have to give a group, a semigroup or a set which satisfies only two laws. So example, so we shall give an example n plus. So we shall check whether it satisfies only two laws. N plus satisfies closure law because sum of any two natural numbers is also a natural number. Similarly, it satisfies associative law. And the next law is identity. Whether it contains an identity element. For example, if we take a natural number 10, what is the number we should add so that we get 10? So that number is 0. So 0 is the identity, but 0 doesn't belong to n. Therefore, identity law fails. Therefore, n plus is a group, but it is not a group. So one example we have given. You can try, you can give another examples also. So next question is, define a finite group, give an example. Define a finite group. So we shall consider a group when we can say it is a finite group if the given set is finite. Okay, we shall write a group G star is said to be a finite group if G is finite. That is, G is a finite set. Okay. So example, so we have already discussed in the previous lectures. So we shall write G is equal to cube roots of unity, or you can write square roots of unity. So G is equal to 1 omega square under multiplication. So you can write the fourth roots of unity under multiplication also. Okay, the next question. Define an infinite group, give an example. So we can write similarly, a group G star is said to be an infinite group if G is infinite. If G is an infinite set, then that group is an infinite group. Example, so same examples which we have given. So Z plus you can write, or you can write Q plus, or you can write R plus, etc. These are all infinite set, but cube roots of unity, square roots of unity, we can't write here because those are all the examples of finite group. Okay, next questions we have. Show that the identity element of a group G is unique. Prove that the inverse of an element of a group G is unique. If G is a group, then prove that A inverse whole inverse is equal to A for all A belongs to G. In a group G, prove that AB whole inverse is equal to B inverse A inverse for all AB belongs to G. So these are all nothing but the properties of groups which we have discussed in the previous lecture. And also you can note here, so in the property we have proved A star B whole inverse is equal to B inverse A inverse. So in case of theorems in groups, we usually consider multiplicative notation, that is AB instead of A star B. We omit star. Therefore, you can omit star here. If you omit star, it becomes AB whole inverse is equal to B inverse A inverse. So since we have proved this in the previous lecture, quickly we shall recall the proof of these questions. Okay, we shall move to next question. Show that the identity element of a group G is its own inverse. Okay, before proving this, we shall consider an example. Once again, I consider Z plus. So what is the identity element here? 0. 0 is the identity element. Okay, what is the inverse of 0? So to find the inverse, write 0 plus what is the element I should add, so that right hand side I get identity. Identity is also 0. Therefore, what is the element I should add? One and only one element is 0. Therefore, inverse of 0 is itself. So how to prove in general? So show that the element of a group G is its own inverse. So we shall write what is given. Given G is a group, let E is the identity element of G, element of G. So instead of is, we shall write B. Okay. And next, to prove that, so what we have to prove? Inverse of identity is itself. That means E inverse is equal to E. Okay, we have to prove like this. Okay, to prove this, we shall consider the identity law. So from the identity law, we have E star E is equal to, so what is the identity law? A star E is equal to A. So that means I should get same element. Therefore I get E here. So now you observe carefully. So what inverse law says? A star A inverse is equal to E. So right hand side, if you get identity element, then A inverse is called the inverse of A, or A is called the inverse of A inverse. Now you see right hand side, we got the identity element. Therefore E is the inverse of E itself. Therefore we have proved that this implies inverse of E is E itself. Okay, we shall move to next question. If every element of a group G is its own inverse, then prove that G is abelian. Or if A square is equal to E for all A belongs to G, then show that G is abelian. Now you see in the first statement, if every element of a group G is its own inverse, that given symbolically as A square is equal to E for all A belongs to G. Okay, we shall consider each separately. Okay, what is given in the first statement? So we shall write given G is a group. So, and in the statement we have every element of a group G is its own inverse. Okay, we shall take two elements, let A and B be any two elements, that is AB belongs to G. So now A and B are any two elements of G. If every element of a group G is its own inverse, means what is the inverse of A? A inverse. What is the inverse of B? B inverse. Therefore this implies A inverse is equal to A and B inverse is equal to B. Okay, now what is our aim? To prove that G is abelian. So what is abelian group? A group which satisfies commutative law. So what is commutative law? A star B is equal to B star A, or without star AB is equal to BA. That means our aim is to prove AB is equal to BA for all AB belongs to G. Now since A and B are any two elements of G, What do you know about G? G is a group. According to closure law, AB also belongs to G. Now AB is an element. Since every element is its own inverse, if I take A, what is inverse of A? A inverse. What is the inverse of B? B inverse. If I take another element C, inverse of C is C inverse. Similarly, what is the inverse of AB? Therefore, this implies inverse of AB is itself, that is AB. Okay, now left hand side we shall use reversal law. So what is reversal law? A star B whole inverse is equal to B inverse star A inverse. So here we have not considered star, therefore this implies B inverse A inverse. Right hand side you write as it is AB. So what is B inverse? B inverse can be written as B, A inverse can be written as A. Therefore this implies in place of B inverse we shall write B, and in place of A inverse we shall write A, and right hand side AB. Or we can write this as, write AB here, which is equal to B, and it is true for all AB belongs to G, and this is nothing but commutative law. So G satisfies commutative law, therefore we can say that G is Abelian. Therefore we have proved. Now we shall consider the another statement. So what is the another statement? If A square is equal to E for all A belongs to G, then we have to show that G is abelian. A square is equal to E is nothing but every element of group G is its own inverse. How? So every element of group G is its own inverse means A inverse is nothing but A. So multiply both sides by A. Therefore, I get A inverse into A is equal to A into A. What is A inverse into A? According to inverse law, it is E. Right hand side we get A square. Therefore, we have A square is equal to E. Okay, now we shall consider. So if they give in the examination the second form, so what is given in the statement? Given. So it is understood G is a group and A square is equal to E for all A belongs to G. So A square is equal to E for all A belongs to G. Suppose if you take B belongs to G, so suppose B is an element of G, then B square is equal to E because of this statement. If I take C, then C square is equal to E. Okay, now A and B are two elements of G. So G means what? G is a group. So in a group means closure law is satisfied. So according to closure law, if A and B belongs to G, AB belongs to G using closure law. So again, according to the given statement, for all A belongs to G, A square is equal to E. So this is an element now. Therefore, this implies AB whole square is equal to E. Okay, now in the next step, we shall write AB whole square. Right hand side I have E. E can be written as E into E because E into E is equal to E. So that is AB whole square is equal to, so one E we shall write it as A square, another E we shall write it as B square. So another E we shall write B square. Okay, left side AB whole square can be written as AB into AB. Right hand side A square can be written as A into A, B square can be written as B into B. So now we shall use associative law on both sides. Therefore we get A of B of E is equal to A of E into B into B. So using left cancellation law, A get cancelled. So remaining is B into AB is equal to A of B into B. So again use associative law. This implies BA into B is equal to AB into B. So again using right cancellation now. Don't forget BA is equal to AB, and this is true for all AB belongs to G. So now we got BA is equal to AB or AB is equal to BA, and it is for all AB belongs to G. So this is nothing but commutative law. Therefore G is abelian. G is abelian. For in both way we can prove G is abelian. Next question is, show that a group G is abelian if and only if, so if and only if the short form is IFF, AB whole square is equal to A square B square for all AB belongs to G. So again, if you get if and only if, we have to prove two cases. So the first case is, in the first case we have to assume G is abelian, and we have to prove AB whole square is equal to A square B square for all AB belongs to G. And the converse part is, we have to assume AB whole square is equal to A square B square, and we have to prove G is abelian. Okay, the first case, suppose G is abelian. G is abelian. So abelian means what? It satisfies commutative law. What is that commutative law? AB is equal to BA for all AB belongs to G. So what is our aim? To prove that AB whole square is equal to A square B square for all AB belongs to G. This statement we have to prove. Okay, now consider the left hand side. The left hand side is AB whole square. Okay, now, or you can write consider. So AB whole square is nothing but AB into AB. Okay, now we shall use associative law. It is nothing but A of B into AB. Again this is equal to, again inside, again use associative law. So this can be written as BA into B. So using associative law we got this step. Okay, but you can see here we have BA. So BA can be written as AB. So that is given. Therefore this is A. BA can be written as AB into B, because that is given. AB is equal to BA. Okay, now this is A of, again use associative law, A of B into B. So that is equal to A of A, and this becomes B square. Again use associative law. This is A into A, B square. Therefore we get A square into B square. Therefore we considered AB whole square and we got A square into B square. Again this is true for all AB belongs to G. So we have proved one case, and we shall prove the converse part. So what is that converse part? So we have to consider. So suppose AB whole square is equal to A square B square for all AB belongs to G. So converse means reverse process. Okay, what is our aim? Prove that G is abelian. Abelian means we have to show G satisfies commutative law. So using this condition. Okay, again we have proved this part earlier. Once again consider that. Consider AB whole square is equal to A square into B square. AB whole square can be written as AB into AB, and A square can be written as A into A, and B square can be written as B into B. Okay, left hand side, use associative law, therefore we get A of B of AB, and right hand side A of A into B into B. So using left cancellation law, A get cancelled, therefore remaining is B into AB is equal to A of B into B. So now again use associative law, this can be written as BA into B is equal to AB into B. So again using right cancellation law, B get cancelled, therefore we get BA is equal to AB, or get AB is equal to B. Again this is true for all AB belongs to G. So what is this? This is nothing but commutative law. Therefore G satisfies commutative law. Therefore G is abelian. Therefore if G is abelian, we can write AB whole square is equal to A square B square for all AB belongs to G. So the next question is, prove that if A square is equal to A, where A belongs to G, then A is equal to E. So what is given? So we shall write first given A square is equal to A, where A belongs to G. And what is to be proved? To prove that A is equal to, so using given condition, we prove A is equal to E. So we consider A square is equal to A. Okay, now left hand side A square can be written as A into A, and right hand side I have only A. Using identity law, we can write A into E. So what is A into E? That is A. Therefore now use left cancellation law. So here we shall write, because AE is equal to A. So using that condition we have written A. Okay, using left cancellation law, what we got? A is equal to E. So using left cancellation law, therefore we have proved A is equal to E. Okay, the next problem. In Z, star is defined by A star B is equal to A plus B plus 1 for all AB belongs to Z. Find the identity element. So again we shall write what is given. A star B is equal to A plus B plus 1. And it is true for all AB belongs to Z. Z is set of all integers. And what is to be found out? To find the identity element. Okay, so from identity law we have, A star E equal to E star A is equal to E, and it is true for all A belongs to G. This is nothing but identity law. But A star E, according to the given, so A star E, so in place of B I have written E. Therefore what happens here? This is equal to A plus E plus 1. But you see left hand side, I have A star E. What is A star E? A star E is nothing but A. This is equal to A plus E plus 1. So I have A here, again A. If you take A left hand side, it becomes A minus A. That becomes 0. Therefore this implies 0 is equal to, remaining is E plus 1. Or we want E, therefore you take plus 1 to the left hand side. Therefore we get E is equal to minus 1. Whether minus 1 belongs to the given set, what is the given set? Set of all integers. Yes, minus 1 belongs to Z. Therefore the identity element is minus 1. So in the examination, they may change the sign. Instead of a plus b plus 1, they may give a plus b minus 1 or a minus b plus 1 or a minus b minus 1, etc. The procedure is same. You can find the identity element. Okay, the next question is, if G is a group of even order, prove that it has an element A not equal to E such that A square is equal to E or A inverse is equal to A. Okay, we shall understand this by considering an example. Okay, take let G be a group of 4 elements. So 4 elements are E, A, B and C. So out of 4 elements, one we must write compulsory, that is identity. So this is the identity element. So what is the order of G or number of elements in G? We have 4. So 4, we know that it is an even number. So I should consider order of G must be even. Okay, now we shall consider these elements E, A, B, C, E, A, B, C. Okay, we know that inverse of identity is itself. Okay, I map the inverse and I have 3 elements remaining A, B, C. Suppose inverse of A, and what is the inverse of B? B inverse of B is A, vice versa. Therefore, inverse of B can't be C. Therefore, only one element is remaining, that is C. Therefore, what is the inverse of C? Inverse of C is itself. So, in general, if G is a group containing elements, what is n here? N is an integer. So if you put n is equal to 1, I get 2. If you put n is equal to 2, I get 4. If you get n is equal to 3, I get 6 and so on. Therefore, G has an even number of elements. Out of n elements, we must have the identity element. So, identity element. So, we know that inverse of identity is itself. Therefore, I remove the identity element from these elements. Therefore, what is the remaining elements? 2n minus 1. So, we have removed the identity. 2n minus 1. 2n is even number. 2n minus 1 is an odd number. Okay, now this is equal to 2n minus 1 can be written as minus 2 plus 1. Okay, from first and the second term, 2 as the common factor. Therefore, we get 2 into n minus 1 and plus 1. So, I have n minus having inverses, or we can say n minus 1 pairs of elements having inverses. But there exists, or there is remaining one element which doesn't have inverse. Therefore, inverse of that element is itself. So, in this example, so what we have considered here, so I have one pair of elements, that is A and B. Inverse of A is B and inverse of B is A. Therefore, one element remains whose inverse is itself. So, we shall prove this problem. So, before that, what is given? Okay, we shall write what is given. So, given G is a group of even order. G group of even order. I hope you understood what the elements of G, the number of elements of G must be even. And what is proved? Is proved there exists an element A belongs to G where A not equal to E, that A must be not an identity element such that A square is equal to E or A inverse is equal to A. So this is our aim. And from this example, we note that inverse of an identity element is self, and every element of G as a unique inverse. Unique inverse means no element has two inverse. Okay, so what we have written? Inverse of identity is itself, and every element of G has a unique inverse. So we get a pair of elements having inverses, and one element is their identity whose inverse is itself. Therefore, there must remain one element such that whose inverse is itself. So, since G is a group of even order, there exists an element. So we shall take that element as A, which is an element of E, and also this is not an identity element, such that inverse is itself. Inverse of this element is itself. Or we can write A square is equal to E. So we get A square is equal to E. For this equation, you multiply both sides by A. Okay, this completes the proof. In the next lecture, we shall consider long answer type questions. Okay, thank you.